All right, let's take a look at the results for the Meme Graveyard Keeper Challenge. So the success rate was 25%. This is actually a little bit off, but only a quarter of the people managed to complete the challenge 100%. And there wasn't too many submissions this time. There was only 12 submissions. So I think the challenge is a little more difficult than the last one. So these are your champions. Round of applause, everybody. Let's get into the actual solution. So you're given, again, like I've established in the previous video, you're given an array of commands, and that's basically just giving you instructions to add to these graves here, these little buckets. So the first number is the amount to add. The second number is the start offset, and the third number is the number of buckets. The naive solution is basically to go over every one of these commands and to just execute them by adding to your buckets. So for the first one here, you'd start here and you'd add 1 and 1 to here. And then for the second one, you would start here and you would add 1, 1, 1, 1. And then for the third one here, you would add 1 to here, 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 and 1 to here. And there you go. There would be your final result. And then you'd run over the entire container and you would take the maximum value, which is 2, and that would be your result. So that's fine, except of course, the number of graves that you can have is the maximum value that can fit in an unsigned int. So that's maximum of 4 billion. So that means for every command, you would potentially have to run over 4 billion elements in a container and perform an add on each one. That's pretty expensive, and that's not going to fit into the time constraints. Now, beyond the fact that it's very slow, if you allocate a container of 4 billion graves, you're going to exceed your maximum limit for storage. So it's very obvious at the beginning that this solution, this naive approach, is not the correct solution. It's impossible for this to work. So there's got to be another way. And the way you do it is, instead of working on graves, you don't create a container for the graves, you work directly on the commands. So what you do is, well, in this command, what it does is it is going to add to the graves. So that means that the point after this command is executed, up until here, so it starts at 0 and it is going to end after container 1. So for this section here, the value is going to be 1. All right, that's the idea. And then when you reach the end of the container here, it's going to go back to 0. But when you reach this one here, it's going to go up by another 1. So now it's at 2. Then when you reach here, it's going to go down, back to 1. But then when you reach this one, it's going to go back up to 1. And then when you reach here, you go down, because it's the end of this range. And then when you reach here, you go down again. So what you do is you go along your commands, and when you reach a command, you add. And when you reach the end of that command range, you subtract. And you just keep track of the current value at the grave. So instead of going over grave by grave by grave, you want to go over command by command by command. Now the problem is, you want to run this in order. So you want to run this in the order that additions and subtractions will happen to your current value. So the order is going to be, well, first this one for an add, then this one for an add, then this one for a subtract, and this one for an add, and then this one for a subtract, and then this one for an add. But the way our commands are going is they are ordered this, this, and this, which isn't going to be the same order. And furthermore, the additions and the subtractions are tied to each other in a single element in our commands. So what we want to do is we want to separate the addition part and subtraction part, separate them all, put them all into a container, and then sort them by their index. So if we split them up and sort them, it'll look something like this. in terms of order. So now we have our first, second, third, fourth, fifth, and sixth delta, or sixth change to our total. And then we just run over our, we run over these guys one by another, one by one, and we say, okay, so for the first one here, we add. And for the second one, we add. And then for the third one, we add and subtract. And then for the fourth one, fifth one, subtract, and then subtract. And we run over that, and we keep track of the biggest value we ever seen, which is going to be 2, and there you go. So this one, you're basically only running over the number of commands times 2. So it's independent of how many graves you have. It doesn't actually matter the graves. The graves just become an index used for sorting this container of deltas. So now your maximum n for your algorithm, instead of being 4 billion, has been reduced to 8 million, because that's the maximum number of commands. So we're 8 million times 2, which would be 16 million. Now, the thing is, you've got a few operations to do here. First, you've got to translate these commands into an array of deltas. So that's basically a big O of n operation. Then you've got to sort your array of deltas. That's n log n. And then you've got to run over your array of deltas, doing additions, keeping track of the running total, and storing the maximum. So that's again a big O of n. So in these 3 steps of the operation, obviously n log n is going to dominate, and that is going to be your sorting operation. So if you want to optimize something, you're probably going to want to optimize this. But yeah, that is basically all there is to it. Now let's take a look at the code. Alright, let's take a look at the code here. Just ignore this if statement for the time being. This code here is what implements that algorithm I just shown you. It's not very long, it's not very complicated. So to start off, we create a vector, and it is a vector of pairs. So we're unsigned int and an int. The unsigned int part gives us the index of the event. These are events, or I like to call them deltas, that will affect the running total, increase it or decrease it, and they signify the beginning or the end of a command range. So the first thing here is the index at which the event happens. The second thing is the amount of increase or decrease. And this one has to be signed, because the increase or decrease can be, obviously if it's a decrease, it's going to be negative. If it's an increase, it's going to be positive. So we do that, and then we reserve some space for the deltas, and the number of deltas is equal to 2 times the number of commands that we have, because every command is going to have a start and an end of the command range. That gives us 2 deltas, the up and the down. So then we run over all of our commands, and we into our deltas, we put the start, which is going to be at the offset, and the quantity, and the end, which is the offset plus the count, and negative of the quantity. And then we sort that guy. Very simple sort. I'll talk about this in a second. But we sort it, and now we have all our commands, and they are going to be sorted in order of their index. And if they have the same index, they're going to be sorted by the amount, the quantity, which is important because you want the negative quantities to happen first. If the positive one happen first, you're going to get the wrong values for your maximums. So you want your negatives always to come first, and this does that automatically. And after you run your sort, you just run over that container, all over the deltas, and you keep a running total. And you also keep track of the maximum that has been seen over the entire running total, and then you return that max and you're done. Super simple. Not that complicated. Now, like I shown you in this diagram here, the dominant part of this algorithm is going to be the sorting part, n log n. And what we can do is we can use something in C++17 called the execution policy. And most algorithms have execution policies, and if you run them with the execution policy parallel, it will try to run your algorithm on multiple cores. So it's going to multi-thread or sort for us automatically. You add this little bit of code in here, you get automatic multi-threading for your sorting, which is the most important part of this algorithm. So, pretty good. And it gives us the fast speed. Now, a few points to go over here quickly. The maximum quantity that any command can have is going to be 2 billion. It's the maximum signed integer. And obviously, if you've got lots of commands, that is going to add up to be greater than 4 billion. And that will overflow out of a normal unsigned int, or definitely a signed int. So you've got to make sure that when you're doing your running total, you use long. You want to use a 64-bit value to do your running total, otherwise you're going to run into problems. So everyone, I think, everyone who submitted, I think they had the correct algorithm. The only problem was they didn't use a long to store up their running result, and therefore they got overflows and they got the wrong answer in the end. So that basically put the separation between the people who just timed out and the people who just outright failed. So it's very important to keep track of your data types, make sure you're not overflowing anywhere. The other thing is, like I said, the order that you sort your deltas in, if they have the same index, it's very important that you put the subtractors in front of the adders. What happens if you put it the other way? Let's try it out. We'll put the adder here, the subtractor here. So now we're going to run over our deltas. And so for the first delta, we're going to add 1. Second delta, we're going to add 1. Third delta, we're going to add 1. So now our max is going to be detected as 3. And then we hit this one, and then we subtract. But it's too late because the max already hit 3. And so our algorithm will return 3. But this is actually happening simultaneously in the same container. So in reality, it doesn't actually reach 3. But because we're running at the 1 delta at a time, it reaches 3 for a small period, and that is a problem. So what you want to do is you want to put your negatives in front of your positives, then it will subtract before it adds, and the end result will be 2 max. So that's another thing, and we get that automatically when we use std pair, because std pair compares the first element, and if the first element is equal, then it will try to order by the second element. So it orders using both elements, and that's fine for us. Now there's one last little optimization we can make. It's kind of a special case optimization. So in general, doing our analysis of our good algorithm here, and log n, right? The bad algorithm is going to be n times f, where f is the field size, or the number of graves. So in general, the number of graves can be from anywhere from 1 to 4 billion, right? So in general, n log n is going to beat out n times f. But what if f is very small, right? Let's say n is 8 million. F is equal to, I don't know, 4. Well, n log n is going to be 8 million times the log 2n of 8 million, which is about 22. So we're looking at, I don't know, 22 times 8, a little under 200 million maybe. That's n log n. N times f is going to be 8 times 4, which is going to be 32 million. So obviously 32 is a much smaller number than 200. So the naive solution will be faster if you have a very small field size. And the comparison is basically, is f less than or equal to, log 2n. And that is more or less where I got this number here. So if field size is greater than 30, we have a sufficiently large field size, we run our normal optimal algorithm. But if the field size is smaller, we're going to run the naive algorithm. We're going to run the naive algorithm for adding, but we're going to run it multi-threaded. So we're going to run 4 threads that each have a section of the commands that they run over. And they're going to build up 4 different sets of graves, 4 different fields. And then at the end, we're going to add those 4 fields together for each grave in the field. And we're going to keep track of the maximum over those. So we process the commands individually over 4 different fields, and then in the end we reduce those 4 different fields to a single field, and we get the max after we've done the reduction. And if we run this, we can see these 2 last tests here, they both have n of 8 million. The first one has a random field size. The second one has I think the first one here has a field size of 4 billion or something. The second one has a field size of 4 or 8, I can't remember, but it's a small field size. And we can see here that with the small field size, using the different code path, it can take advantage of that, and it's 10 times faster than the optimal solution for large field sizes. So this special case here is something you'd have to consider if you want to get optimal performance in the special case of a small f problem. And there you have it. There is the meme graveyard keeper complete. Hats off to all our champions here. And yeah, no, I mean, I got some messages at the beginning when I posted the challenge, and some people were like, well, this is so easy, I'm not even going to try it. And looking at the results, it seems like it was more difficult than the last one. So a lot of people, when they see the problem, when they see me present it, they don't actually think about it. They don't have the depth of thought to actually see the real problem. They just see it and they say, oh, I could do that. I could just run over the commands, add them to an array of graves. This is easy. This is, you know, high school programming. But nah, you've got to see the problem. You got to realize it's never going to be that easy. There's always going to be a trick. And if you want to improve on the solution more than this, you pretty much going to have to write your own sorting algorithm that can beat the standard library, because this is the weak link of the chain. This is where you'll get the biggest improvement. And this sorting algorithm, this execution policy here, it's parallel unsequence. So what that means is that this will allow the standard library to multi-thread and to vectorize. But as far as I know, there is no library, especially not Visual Studio, that will vectorize a sorting operation like this. So if you can manage to make a fast vectorized sorting that would beat the standard library implementation, then you could probably beat my implementation here. The other way to try to beat it is to do it exactly the same, but then to try to multi-thread or vectorize things like this final step here or this step here, something like that. They don't mean much, but this little bit of extra you get could be enough to, you know, beat me if you wanted to. But I wasn't about to waste, you know, a lot of, you know, potentially hours vectorizing this stuff for very little gain. So I just did the standard thing that I could think of, called it a day, and it was good enough. It was good enough. Anyways, thanks for watching. Hope you enjoyed the video. If you did, please click the like button, and I will see you soon with some more coding challenges.